Okay, can you hear me on the Zoom chat? Hello, can you hear me on the Zoom chat? All right, good. All right. For some reason, it just resets the audio. It should be in the recording, so it should be okay. If there's any weirdness about it, let me know. I have alternate videos where I did this for the high school. So I can upload those instead. And I'll get videos uploaded this evening right after class. These things, it takes a minute for Zoom to process them. And my internet's bad at home, so there may be a delay in it. That's okay. We'll get there. So a lot of the next couple of weeks, the next week is going to be how musical instruments work. And the start is going to be stringed instruments. The start's going to be guitars, pianos, harps, that sort of stuff. And this also works for other things. But generally stringed instruments. The gist is something that is a very one-dimensional object oscillating. All right, and the gist of it is when we send a wave, this is a preview of what's going on. Here's our string. It's really going to look something like a wave that looks like this over time. Is not going to look like a squiggle. It's going to maybe at best look like chunks of waves like that. Is that the wave kind of just reflects backwards off of the fixed points, and it builds this structure, what's called a standing wave. We'll talk about standing waves more later. So in your mind, you don't have to worry about the wave propagating. It more of just builds up a resonance. But anyway, we have a transverse wave that's going to travel down the length of this string. And we have a length. Here is 0.628 meters. That's determined by what note you want to play. In this case, we're trying to play low E and high E on the guitar. So that's a fat string and a thin string, the bottom and top string. And then we have masses. All right, and the low string is generally heavier than the high string. That's what you would see. That's what is required for the required to play the particular note. And you turn the pegs to change the tension. So the tension force here is given. And then the question is, well, how do we find speeds? Well, the first step is to know that mass per unit length, or to use the formula that uses it. So this mass per unit length is mass per length. And so we have, let's do the low string. Sorry, the low string is 3.32 grams. And then, so that's going to give you something in grams per meter. And you want to convert that to kilograms per meter. So it's going to be times 1 kilogram per 1,000 grams. So that's the first part. And then the second part is going to be V is square root F over mu. And F here, so F here is our 226 newtons. And so we're just going to plug that in. And so a lot of these equations is the problem is identifying the number you need. This mass per unit length is often not calculated ahead of time. Or sometimes it is. Sometimes it's, you don't know the mass or the length, but you know the density. So we'll go ahead to the next slide, which should have the calculation here. For the high E, all right, we do this calculation. They converted to kilograms of mass immediately. And so for high E, you get the velocity in the medium is about 820 meters a second. And in low E, it's about 200 meters a second. And what you'll note is, just as a check of your math, all right, the high E and low E are about an octave apart. And so the that means you're going to double the frequency eventually. You're not changing the wavelength any because that's the fixed length. Actually, you are changing it. You're doubling the, you're halving the wavelength. The gist of it is looking at these numbers. Do they make sense? Well, one's 4 times the other. And maybe it makes sense. Seems okay. Like there's, your intuition is, one thing that's kind of reasonable is it's around the speed of sound. It's not overly low or overly high. So anyway, yeah, sometimes intuition with these problems, eventually we'll get to a point where, as we go through the class, we just don't have intuition at all. And this is kind of getting close to it. All right, so we have another question here. Imagine that we have a rope hanging down from the ceiling. Imagine a bell rope in a church. So you have a big bell, 40, 50 feet up, and then this rope that's strong enough to move the bell is hanging down, and you shake the bottom end of it. So it has a transverse wave going up the rope. And the question that I have, so you're going to have to imagine this in your mind. As it travels up the rope, does it speed up, does it slow down, or does it travel at the same rate? And so I'm going to give you a second to think about it, and then I'll ask, and then we'll go over it for a minute. We'll draw a little picture here and think about the problem. So there's nothing at the bottom end of the rope. That's kind of the important bit is you don't see any, there's no weight to give it tension immediately. So the question is, where is that tension coming from? All right. Not too many of you in here. Who says that it increases? Who says that it decreases? Remains the same? All right, a lot of hands for remains the same. Who will just admit they don't know? Okay, so we draw the rope, and this is the thing, it is a real rope. Most of the time when we talk about a string, rope, cable, something like that, we assume it's massless relative to the other masses in the problem. Right? We always use like a tow rope to tow a car. The tow rope is massless compared to the car. It's a couple of pounds versus a couple thousand pounds. Here, there's no other mass. So when we start the wave here, we have some velocity there. Now, when it's up here, we're looking at this chunk as it's moving this way. So we'll call this V initial at the bottom. Now, at this chunk, this is the mass that causes tension. All right, there's our forces on it. There's a tension from the rope above, there's a tension from the rope below, which is not much, and there's the mass of that chunk. Now, effectively, this chunk causes this pattern. If we move up, all right, so there's our rope. If we move up to this chunk, so mass 1, mass 2. Mass 2 is larger than mass 1. which means there's a higher tension. So at this point, this velocity is greater than the initial, and because our tension is increasing. And then this V2 is greater than V1, again, because our tension is increasing. So as it travels up the rope, there is more mass below, creating tension in the rope. All right, so effectively, the tension at the lower parts of a real rope is lower than the tension at the higher parts. All right, because the bottom of the rope doesn't have to hold anything. The top of the rope has to hold the entire rope. So it has to go up effectively linearly as you go up the rope. And so the tension increases, and all right, so in this function, it's not a linear proportionality, but the velocity is proportional to the frequency. It's directly proportional. So if the tension goes up, the velocity has to also go up. And so that's our solution, is that it increases. All right, so now we can do an example problem where we actually put a weight at the end of this rope. All right, we hang a weight on the end of this long wire. We can ignore the mass of the wire to figure out the tension. All the tension is coming from this bob. And so the pendulum bob causes a tension on the wire, and then we strike the wire and we ask, how long does it take for the pulse to travel? And so we know that this has a length. So the idea is that we want to find the time it takes to travel. To do that, we would need to find the velocity and then do simple velocity as distance over time. So to find the velocity, all right, our goal is to find the velocity is from the force and the mass per unit length, sorry, the tension force, and that's just going to be distance over time. All right, so we can go through and do that calculation. I'm going to try to do it here because I don't have the actual solutions in front of me. Because I put this slide in, I didn't put solution slides. So the gist of it is the mass per unit length. Well, we have 2 grams is 0.002 kilograms, and we have 3 meters. And then we pull up a calculator. What? Okay. And that would be 6.7 times 10 to the minus 4 kilograms per meter. So now we can plug it in here, except we don't know what the tension is. So we have to find the tension. And this is where we do a free body diagram for this mass. And so the tension here is going to be the weight. And so it's going to be 1.2 kilograms times 9.8 meters per second squared. So let's see. I want to do 1.2 times 9.8. And so we have 11.8 newtons. And so now we can do this calculation is 11.8 newtons per 6.7 times 10 to the minus 4 kilograms per meter. And what I will do is separate out these calculations carefully like that. So to get our velocity, we do this division. We take the square root. So get a big number, take square root. The velocity is about 132. 132.5. And I'm rounding to 3 sig figs. And it's below, yeah. So now our time is distance divided by velocity from rearranging this. Times distance divided by velocity. So it's 3 meters divided by this. And what we get is 0.02 seconds, about 20 milliseconds. All right, if you're working this in your own notes, does it make sense? So you kind of have to break some of these problems down is when you're doing these things, you know, realize that when we give you a setup that looks like you're putting tension on a string, you're probably looking for velocity from tension on a string. All right, so I'll keep going from here. So we're not going to do a lot of examples for the rest of this immediately. I kind of have to define a few things based on what you saw in 111. But in any case, the velocity of the wave always depends on what the wave's going through. And so you can calculate it from material properties. We saw the example for a string for a one-dimensional object. If it's three-dimensional, then we have to look for things that are the analogs, you know, of tension here and linear density. We have to look for analogs of those. And so for liquids, I don't know if we covered this in 111. I know my class at least mentioned it and it did nothing with it. There's a property for a fluid called the bulk modulus. And it has to do with effectively the pressure of the fluid will cause some change in the volume of an object. If you push, you know, say you have a submarine and you put the submarine in water, at the surface it's one size in volume, but as you let it sink down, it gets pressed inwards. And so the volume of your submarine depends on the bulk modulus for steel and for other, you know, air and whatever else is in the submarine. But that also applies to the fluid. The fluid compresses as you go deeper. Most of the time we pretend it's incompressible, but it's not. It has a bulk modulus. And this is, in a sense, the force of the material acting like a spring, pushing outwards. And it also has a density, which is analogous to the linear density. Now it's a density in all directions. So for a solid, you get the same thing. So for these things, these are materials, solids and fluids, acting under Hooke's law. So if you want to know more about this, you can go back and look at when we talked about springs in 111 and look for Hooke's law. And this is the hard detail. But just as solids have a stretching or compressing, so along their length property called Young's modulus. They also have a side-to-side perpendicular to their length number called the shear modulus. But in this case, what we care about is the wave moving in some direction. We care about Young's modulus in that direction and the density. Now these things, as far as this class, they are effectively things you look up. All right, so you know, there's a chart of mass density, there's a chart of bulk modulus and Young's modulus, which interestingly look a lot like pressure because they depend on, all right, so this formula, Y, looks like the force per unit area times the change in length per length initially. So the amount, basically the proportion that the object changes in length because it feels pressure times the pressure that it feels. All right, so you can go look that up. But ultimately, if you wanted to calculate it, you could, but ultimately just look it up in a chart. And if we ever want you to do that, I'll give you these numbers so you can do it. All right, now I didn't mention anything at all about gases. Gases are special. And in 2 weeks, we'll start. Who in here is taking chemistry or something like it where you deal with ideal gases? That's what we're doing. So I am going to cover a tiny little bit today so that the formulas that I talk about make sense. But we're going to talk about sound waves. All right, now it is imagine you're pushing on a slinky in its direction, causing longitudinal waves. That's what you're doing with sound. Here we have a speaker, and the speaker pushes, so it compresses the gas, and then the speaker will pull back and causes a vacuum in the gas. And so it alternates, it changes the pressure in the gas. And so you get a wave that propagates outwards. And so it bunches up. And in this case, we can identify this is effectively your wavelength. Your amplitude is a change in the pressure. That's already drawn on the slide. Why did I draw it? But you can identify the properties of a wave in the sound in looking at the pressure in a small area as the wave passes by. All right, you'd have a chart that's effectively the change in pressure and position, and it looks something like a sine wave, just like you would expect. So the important thing to note is that it's not a flow of air, right? In all other waves, the particles in the medium stay put. They just oscillate back and forth. They don't flow. But that oscillation, what happens, in the places where it is compressed, you have forces outwards into the places where it's rarefacted, not compressed, where it's few particles. And so the places that have few particles will eventually gather particles and turn into places that's compressed, and vice versa. So frequency for sound is the same as it is for other waves. It's the number of cycles per second. And, so when I talk to you, there's lots of different frequencies in my voice. I have a kind of irritating high voice to my ear. But, there's lots of tones in it. And that's the truth for y'all. It's rather hard to generate as a person a single tone. But if you have a single frequency, something like the dial tone buttons on a phone, that's what's called a pure tone. If you ever listen to those, when you dial a number and you hear the tones, those tones are there for a reason. They're to signal to the phone company what number you're dialing. Right? Is that they don't understand what button you've pushed, and it's your cell phone has to work with landlines, and the landline system detected by a combination of tones. So when you hear tones, you determine the pitch, you determine the note that's being played. All right. So if you listen to some of these, Some of these are fairly close to actual tones that you would hear, and some of them aren't. They're very, but you know, if you've ever sit there and poked numbers at your phone and played music, that's what you're doing. All right, so I've talked about the pressure amplitude. To your perspective, that is the loudness of a tone. And we'll talk about this next week when we talk about musical instruments and talk about standing waves. Effectively, your ear is a instrument. It's a thing that holds standing waves in it. And so there is a component of this that's subjective. Loudness depends on whether the sound will resonate with your ear, but it also depends on the amplitude. Effectively, the more change in pressure you can get, the louder the sound will be. So we can derive the speed of sound, but we'll just give you some numbers up front. And effectively, sound travels through different mediums at different speeds. And we have here air. It's kind of important. We'll use that a lot. And it varies with temperature. Note that 0 degrees, it's lower than 20 degrees. There is a formula for calculating that. We don't care. Carbon dioxide is particularly lower. I don't know if anyone's seen this on YouTube. There's a couple of videos going around where they fill a beach ball with carbon dioxide and they use it as basically a lens. They focus sound to different places. It's kind of weird. But note that, gases are all around 300 to 1,000 meters per second. Then liquids are all above that. Right? If you've been, if you've been swimming and you've been underwater and you hear people, they sound different because the waves that are coming through the air go into the water and then they speed up. And so they sound different. And then solids are even more sped up. This is the thing about putting your ear to the ground and hearing stuff before you can hear it through the air because the waves are traveling faster. So if you want to calculate it, this is where the formula comes from. It comes from an ideal gas. It depends on what the gas is. In particular, these are the divisions. You use this constant in here is 5/3 if it's a single atom gas, something like helium or neon, where it doesn't form a compound. And it's 7/5 if it does form a compound. And it may be a different number if it's a complex compound, like say gasoline vapor. That is a hugely complex compound. So it might be different for that, but we'll basically say, does it form a compound? Use 7/5. Does it not? Use 5/3. And that comes from chemistry. You can deal with the chemist about that. We're not going to go into it right now. The particles themselves, like if you are in a quiet room, the particles themselves are moving and they have an average speed that looks like this term down here. We'll go over where that comes from. But the energy that is carried by the sound wave goes based on this function, which involves the temperature of the gas. So that completes all the different ways you could possibly calculate the speed of a wave in a material. So I do want to point out is there's a speed of sound in things like solids and liquids, and they are possibly different from the speed of a wave, imagine a long stick, like a PVC pipe, something that's about 10 foot long. If you cause sound to travel through it, that's one sort of wave. Have longitudinal and transverse components possibly, but you're shaking the individual atoms. There is also just shaking the pipe up and down and causing it and treating it like a string, a one-dimensional object. So you could possibly have multiple types of waves, but we'll generally tell you what you're supposed to deal with. All right, so we have this example of in elementary school. Did anyone tell you about this rule? Like that was a thing because Channel 7 used to go around the schools and talk about weather. And so that was kind of a big thing when that was 20 some years ago, 25, 30 years ago now. But the gist of it is there's a rule of thumb for figuring out how far away a storm is. And it has to work with miles, right? So generally the idea is if we go back to the speed of sound charts, all right, the speed of sound in air is about 300 meters per second. The speed of sound in solids is going to be at least 5 times that, but it turns out that in regular dirt, no, that's not what I'm talking about, sorry. Yeah, so the speed of sound is a fixed number and it's small. The speed of light is huge. So effectively, when you see a storm, when you see lightning hit, you see the flash immediately. But it turns out that the speed of sound in terms of, well, here's the number I wanted. A mile is about 1,500 meters. And the speed of sound is about 300 meters per second. What? Go away. Go away. So effectively, every 5 seconds is about 1 mile. Because every 5 seconds is 1,500 meters. Does that make sense to you guys? Sometimes I wonder if I'm explaining things weirdly to my head. I say it and I'm like, no, that doesn't make no sense at all. Sometimes I catch myself and sometimes. This is an example. Let's see, let me see if there's any. All right, we'll talk about some of these. So these are all problems that use V is gamma KT over the mass. So they're all problems that look like that. Okay. So we're going to skip these because I haven't introduced some stuff. It comes from next week's stuff. So you need to know what that is, what the molecular mass is. That is a unit. One atomic mass unit is 10 to the minus 27 kilograms. So we're going to skip problems like that. And we're going to skip problems like this. We'll bring those up in in next week's work. This is a problem we could do in principle. Scuba divers below a boat. So we draw it out. This distance is 10 meters. Then there's a siren that is 3 meters. And we can ask how long it takes the sound to travel. All right, so the gist of this is there's 2 mediums. And so there's 2 ways, there's 2 sort of chunks. We have to figure out this time, which is distance divided by velocity. So 3 meters divided by 340 meters per second. Then we have to figure out this chunk, how long it takes to go through the water. And that's 10 meters divided by, let's go back and find liquids, fresh water, we'll take 1,500. And then you would add those two times up and get the total. So problems like that, is realizing that the wave is possibly going through two different materials. How do I deal with that? And in that case, we didn't need to do anything with calculating based on, like the density of air or water or anything. So that's, I think, what I wanted to cover today for the homework this week. I'm going to stop sharing. I'm going to pull up next week's slides because I want to introduce the lab for next week. All right. So share the screen, share waves part 2. So next week, we're going to talk about what happens when waves from more than one source meet. And so effectively, let's see, this is two sources. Standing waves come from reflection. And then Doppler effect is weird. I'm going to save that right now. But what I want to get into is, well, we add waves together, weird things happen. But in particular, in the lab, we're going to have actual slinkies or actual springs, and we're going to send pulses along the springs. And we're going to ask what happens. And so essentially what I want to say is if I have a particular chunk of the wave, I can ask how much energy is in it. Those things have the same amplitude, so they have about the same energy. We'll call it E1 and E2. When they meet, we can ask, well, how much energy is there? Well, it's E1 plus E2, which means twice the energy, twice the amplitude, we would think. And so when waves meet like this, you see that they constructively interfere. And so we're going to ask you to show that in the lab. But now there's a trick here, is the energy is not a vector, it's a scalar number. It's a number, and of course it just adds up. But the energy is proportional to the amplitude squared, and the amplitude is a vector. It has a direction. We can say here that the amplitude is up. Skip this. Here, we have an amplitude that's down and an amplitude that's up. So the amplitude is negative. And so the energy still adds up because it's still the amplitude squared, so it's still a positive number. But the actual displacement of the wave changes. Here we have that it goes up, and here that we have that it goes down. And we're basically subtracting, we're taking A plus minus A, and we end up with that it cancels out. The energy's still there because at the instant that it's canceled out, it still has velocity, so it's going to keep moving. It just doesn't, at the moment, have any deflection from equilibrium. So we're going to talk about constructive and destructive interference like this, and you're going to try to show that happens. That's the gist of linear superposition. The idea is that when we add two waves, we're just going to add their amplitudes. I'm trying to find a problem that you'll actually practice with, but I'm not seeing it here. Here it is. If we have two waves meeting like this, you're going to have this problem in the lab where these waves are going to overlap eventually. So if it's moving 2 centimeters a second, then half a second later, it's moved 1 centimeter. So this part of the wave that is upwards looks like that. And then in a different color, this part of the wave has moved that way. So in half a second, it's moved 1 set of squares. That's bad. It's close enough. But the gist of it is, let's pick a point like here and here. We would add these amplitudes up. That's about 2 squares up. This is about 2.5 squares down, maybe 3 squares down. The gist of it is the actual point on the spring would be there. Until this thing adding up would look something like that, like the line in blue. And the idea is that it would be a matter of counting squares. And so it'll make more sense when we get in the lab and you actually do it. All right, so I'm just introducing the lab. Next week is going to be what happens when waves reflect and what happens when 2 waves meet and add up. How do they interact with each other? So that's what we're going to do for the labs. This is where I want to stop for the day. I have a good amount of time here to answer homework questions if you have them. Let me take care of stopping the Zoom, stopping the recording and such. And if you have questions, we'll go over homework